Hello everyone, let's start periodic properties. The periodic table is the framework upon which much of our understanding of inorganic chemistry is based. In this chapter, we will provide the basic properties that you will need for more detailed discussion of main group elements in later chapters. Long form of the periodic table. In the modern periodic table, the elements are arranged in order of their increasing atomic orbitals. There have been several designs of the table over the years, but the two most common designs are the long form and the short form. The long form of the periodic table shows all the elements in numerical order. However, the long form is a very elongated and cumbersome diagram because elements from lanthanum to ytterbium and from actinium to nobelium show similar chemical behavior. The short form cleverly displays these two sets of elements in rows below the remainder of the table, and the resulting space is closed. The new compact short form of the table is shown in figure 2.2. The long form of the periodic table consists of horizontal rows called periods and vertical columns called the groups. A period is comprised of series of elements that atoms of which possesses the same number of electron shell. That is principal quantum number. The number of elements in each period corresponds to the number of electrons required to fill those orbitals as shown in figure. In a particular period, the principal quantum number of the p orbitals the same as that of s orbitals, where the d orbitals are 1 less and the f orbitals are 2 less. The main group corresponding to elements in which the s and p orbitals are being filled. In the periodic table, there are 7 periods and each period starts with a new principal quantum number. It is important to mention that the first 6 periods are full, contain 2, 8, 18, 18 and 32 electrons respectively, while the 7th period is incomplete and contains 26 elements. It has a maximum capacity of 32 elements. The first 3 periods containing 2, 8 and 8 elements are called short periods, while the next 3 contains 18, 18, 32 elements are called long periods. The vertical columns are called groups. Each group contains elements of similar electronic configuration. For example, all group 1 elements have one outer electron, that is ns1, where n is the principal quantum number. Although elements in group have similar properties, it is important to realize that every element is unique. For example, nitrogen and phosphorus are elements of the same group. Nitrogen gas is very unreactive and phosphorus is highly reactive and spontaneously catches fire in air. There are in total 18 groups in the long form of the periodic table. According to recommendations of International Union of Pure and Applied Chemistry, the groups of elements are numbered from 1 to 18. Earlier, the groups were numbered from 1 to 8 as A and B groups. IUPAC has replaced the old system of using a mixture of Roman numerals and letters. The notations caused some confusion because of differences in numbering between USA and rest of the world. As an example, in USA, the group refers of group containing scandium, whereas in the rest of the world, this designation was used for group starting from boron. Group 1 and 2 and group 13 to 18 elements, the main group elements, the group 3 to 11 are classified as transition metals. In the transition metals, the d orbitals are progressively filled. We shall be focusing in this course on the chemistry of main group elements. The elements of group 12, although included in the transition metals, have a very different chemistry. Some of the groups have got special names. For example, alkali metals, alkaline earth metals, chalcogens, halogens and noble gases. The elements of group 11 are called coinage metals. The elements corresponding to the filling 4f orbitals are called lanthanoids, and those corresponding to 5f orbitals are called actinoids. Earlier these were named lanthanides and actinides, but the ending IDE is not justified as IDE is generally used in the end of anions. Example, oxide, chloride. Initially, IUPAC suggested the names as lanthans and actinons. However, later, this was not finally accepted as the ending on is preferred only for non-metals, example boron, silicon, etc. Whereas lanthanides and actinides are metallic in nature. Finally, the word lanthanoid and actinoid is recommended and should be strictly followed. S, P, D and F block of elements. The long form of periodic table can be conventionally divided into 4 main blocks. S block elements, the elements in which the last electron enters the s orbitals of their outermost energy level, are called s block elements. There are 2 groups in this block Y with electronic configuration ns1 and ns2. The general electronic configuration is ns1 to 2. P block elements, the elements in which the last electron enters the p orbitals of their outermost energy level, are called p block elements. The general electronic configuration of p block elements may be written as ns2 and p1 to 6. All the elements of group 13 to 18 constitute p block elements. D block elements, the elements in which the last electron enters the d orbitals of their penultimate energy level, constitute D block elements. These elements are called transition elements. It is because these elements symbolize a change in the character from the metals on one side to non-metals. Thus, these elements lie in between S and P elements and form 10 groups. These groups are named from 3 to 12. In the general, the electronic configuration of D block elements may be represented as n-1, D1 to 10, ns1 or 2. The D block elements contain 3 complete rows of 10 elements, which involves the filling of 3d, 4d and 5d orbitals respectively. Elements starting from scandium to zinc constitute the first transition series. Elements starting from yttrium and ending the cadmium constitute the second transition series, while elements starting from lanthanum, hafnium to mercury is called third transition series. F block elements. The elements in which the last electron enters the f orbitals of their atoms are called F block elements. The last electron enters into the third to the outermost energy level, that is n-2f. There are 2 series in the block of elements and are separately placed at the bottom of the periodic table. The first series starts with lanthanum, and the elements present in this series are called lanthanoids. The second series starts with element actinium and ends up with element Lr103. The elements of this series are called actinoids. The general electronic configuration of these elements may be represented as n-2f1 to 14, n-1d021 and ns2. Effective nuclear charge and Slater's rules. We have already discussed that in a multi-electron atoms, the electrons in the outermost shell do not experience the full effect of the nucleus. This is primarily because of the intervening electrons that come in the way between the nucleus and the outermost electrons of the atom. In other words, the inner core of electrons act as a barrier between the nucleus and the outermost electrons. As a result, the outer electrons experience only a part of the nuclear charge. The actual nuclear charge felt by the outermost electron is called effective nuclear charge, which is lower than the total nuclear charge. Since the inner electrons serve as a shield or a screen, this effect is called shielding or screening effect. Thus, the effective nuclear charge at start can be easily expressed by subtracting the shielding or screening effect for the inner electrons from the actual nuclear charge. In 1930, J.C. Slater proposed a set of empirical rules to calculate the effective nuclear charge. These rules are solely based upon the penetration power of the various orbitals. We have already learned in chapter 1 that S electrons tends to share the nucleus more effectively than P electrons, which in turn will share the nucleus more effectively than D electrons. Thus, for a given value of n, the screening constant S varies as S greater than P greater than D greater than F. Periodic properties. Atomic properties, which can be used to explain periodicity of chemical and physical properties, must also be periodic in nature. We would expect atomic properties to be related to the observed periodicity in the electronic configuration of atoms. We shall examine 4 of the important atomic properties that are most useful in explaining chemical and physical properties. These are atomic and ionic radii, ionization energy, electron affinity and electronegativity. Atomic and ionic radii. Atomic size. One of the most important systematically periodic properties is atomic and ionic radius. We have learned in the previous chapter that electrons can be defined only in terms of probability, and therefore there is no real boundary ascribed to an atom. In other words, the electron cloud around the nucleus do not have sharp defined boundary. Thus, atom and ions cannot be regarded as hard walls. How can then we define the size of the atom or ion? These are actually 4 ways to determine the size of the atom, and to some extent they give different values. One of the simplest methods to define the atomic radius is to measure the distance between the nucleus and the outermost shell of the atom or ion. Let us take a simple homonuclear diatomic molecule such as chlorine. The radius of chlorine atom can be determined experimentally by dividing the distance between the centers of 2 atoms in chlorine molecule by 2. The distance is 2 ampere, so the radius of chlorine atom is 100 picometer. The distance is also called the covalent radius because the atoms are held together by a covalent bond. Similarly, the CC distance in diamond is 1.54 Armstrong, that is 154 picometer. So the radius of carbon atom is 77 picometer. In order to test the accuracy of this method, we can add them together to estimate the distance between the chlorine and carbon in a molecule, say carbon tetrachloride. The carbon chlorine distance comes out to be 177. The distance is in close agreement with the experimentally determined distance of 176 picometer. The radius of an atom is calculated by measuring the distance between the centers of two atoms in a molecule with the help of X-ray diffraction spectral studies. Thus, in case of homonuclear diatomic molecules, the covalent radius is defined as one half of the distance between the center of nuclei of two similar atoms bonded in a molecule. Similarly, in a heteronuclear diatomic molecule, the singly bonded covalent radius of an atom can be calculated by knowing the internuclear distance between the two nuclei and covalent radius of the other atom. For example, the internuclear distance between iodine and chlorine in ICl bond is 2.32 Armstrong. The reader is advised to consult article 1.14 of chapter 1 for detailed discussion. Ri plus RCl is 2.32 Armstrong. Ri plus 1 Armstrong is equal to 2.32 Armstrong. Ri is equals to 1.32 Armstrong. Thus, the covalent radius of iodine is 1.32 Armstrong. This approach of determining the radii of ions is applicable in molecular compounds of the elements that exist as singly bonded. The atomic radii of atoms which do not form diatomic molecules with single bonds are calculated by indirect method. For example, the single bond radii of nitrogen and oxygen cannot be obtained from the bond lengths in triply bonded like N2 and doubly bonded O2 molecules. This is because these molecules can contain multiple bonds. The single bond atomic radius of nitrogen can be obtained indirectly. For example, the internuclear distance between CN in CH3NH2 has been found to be 1.47 Armstrong. We know the atomic radius of carbon in diamond is 0.77 Armstrong. Therefore, the atomic radius of nitrogen in CN bond is 0.70 Armstrong. The simple rule of evaluating the atomic radius is true in cases where the bonds formed between the atoms are singly covalent. The difference in electronegativity of bonded atoms is not large. However, in cases where there is large difference in electronegativities, Komaker and Stevenson proposed a new equation for calculating covalent radius. That is RAB is equals to RA plus RB minus CXA minus XB, where RAB is the internuclear distance between A and B. RA and RB are the covalent radii of A and B, while X and XB are the electronegativities of A and B respectively. C is constant, have the values 0.08, 0.06, 0.04 and 0.024 elements, second, third, fourth and fifth periods of P block elements respectively. In going from top to bottom of the periodic table, the outermost electrons are placed in orbitals with higher and higher values of principal quantum number n. The higher the principal quantum number of the shell, the larger is the radii of the shell. Although the charge on the nucleus increases going down a group, the effective nuclear charge, that is the actual charge experienced by outer electrons, does not increase as much. For example, the atomic number of lithium is 3 and the atomic number of K is 19. The positive charge in the nucleus of a potassium atom is over 6 times as large as the positive charge on the nucleus of lithium atom. However, the effective nuclear charge that the electron in a potassium atom feels is less than the 3 times the effective nuclear charge that the outer electron of a lithium atom feels. In a potassium ion, there are more electrons between the nucleus and the outer electrons to shield the outer electrons from the positive charge in the nucleus. The increase in size with an increase in principal quantum number predominates over increasing effective nuclear charge, and the atomic radius increase in going down a group. The atomic radii of main group elements decrease from left to right across the period in the periodic table. The principal quantum number of the outer electrons is the same all across a period. The outer electrons are in the same cell. Electrons added to the outer shell do not shield other outer electrons from the positive charge of the nucleus very well. On the other hand, the charge of the nucleus increases from left to right of the periodic table across the period in the periodic table. As a result, the outer electrons are attracted more strongly and pulled in towards the nucleus, making the atom smaller. The periodic trend in the atomic radii of transition metal atom is somewhat different from that of main group elements. Going from left to right across a given period, the radii initially decrease across the first few elements. The sizes of the elements in the middle of the transition series then changes very little until a small increase in size occurs at the end of series. The size of the atom is determined largely by electrons in the outermost shell, that is by the electrons of the ns subshell in the first transition series. For example, the outer shell electrons, the 4s electrons, but electrons are being added to the 3d orbital across the series. The increased nuclear charge on the atoms as one moves from left to right should cause the radius to decrease. This effect, however, is mostly cancelled out by increased electron-electron repulsion among the electrons. On reaching group 11 and 12 elements at the end of series, the size increases slightly because the d subshell is filled and the electron-electron repulsion causes the size to increase. Radii in multiple bonded atoms. In case of multiple bonded atoms, radii are named multiple bond radii. For example, the radii in ethylene and acetylene are named as double bonded and triple bonded radii respectively. Multiple bonds are shorter than single bonds between the same pairs of atoms because the additional bonding electrons pulls the atom close together. Let us compare the length of various carbon-carbon bonds. Hybridization and atomic radius. The atomic radius of an atom also depends upon the type of hybridization used by the concerned atom. For example, the atomic radius of carbon is different in methane, ethene, and acetylene. Ionic and crystal radii. The ionic radii refers to the radius of ions in an ionic crystal. The ions are formed by the loss or gain of electrons from the outermost shell of atoms. The ions referred by the loss of electrons are called the cations, whereas ions formed by the gain of electrons are called anions. Metals usually form positive ions. When an electron is removed from the atoms to form the cation, the size shrinks considerably. Thus, the radius of the cation is always smaller than that of the atom from which it is derived. For example, the radius of lithium is 1.52 Armstrong, whereas that of lithium ion is only 0.9 Armstrong, that is 90 picometer. This is because when an electron is removed from an atom, the attractive force of the nucleus on the remaining electrons increases. This results in the decrease in size of the ion. In the above example, the loss of 2s electrons from the lithium leaves lithium ion Li positive with no electron in the n is equals to 2 shell. The decrease in size will be more in cases where 2 or more electrons are removed. For example, in case of aluminium 3 positive, the size reduces to almost 50% of the neutral aluminium ion. Radius of aluminium is 143 picometer and Al3 positive radius is 68 picometer. The anions, on the other hand, are always larger than the atoms from which they are derived. Here, the explanation is just opposite to that used in the case of cations. For example, the fluorine atom has 9 protons and 9 electrons. On the forming the anion, the nuclear charge is still plus 9, but where are 10 electrons in the anion? Thus, the fluoride ion F negative is much larger than the F atom because of increased electron-electron repulsion. Determination of ionic radius. A number of methods are known to determine the ionic radii of ions, but Pauling's method is the most widely accepted method. However, this method is limited to univalent isoelectronic ions. This method is based upon the observed internuclear separating in 4 crystals, namely as NAF, KCl, RBBr, and CSI. These compounds were selected by Pauling because they have almost the same radius ratio, nearly equal ionic character. In each case, the cation and anion are isoelectronic. Two basic assumptions were made by Pauling while assigning radii to the individual atoms. The cations and anions are assumed to be in contact, that is R plus R negative is equals to R, that is internuclear distance. The radius of the ion is inversely proportional to the effective nuclear charge of ion. R effective is inversely proportional to 1 by Z effective. We know Z effective is equals to Z minus S, where Z is the atomic number of the atom and S is the screening or shielding constant. R ion is inversely proportional to 1 upon Z minus S, where C is the proportionality constant and has the same value for 2 electronic ions. Let us take a particular example of sodium fluoride to explain the concept of Pauling for evaluating the ionic radii. The internuclear distance in NAF has been experimentally determined by X-ray technique to be 2.31 Armstrong. Thus, RNA positive plus RCl negative is 2.31 Armstrong. First assumption of Pauling. Now both Na positive and F negative ions are isoelectronic, that is both have 10 electrons and consequently have the same screening constant. The effective nuclear charge on Na positive and F negative can be calculated by subtracting the screening constant from the actual nuclear charge. Effective nuclear charge on Na positive is equals to ZNA minus screening constant, that is 11 minus 2 into 0.85 plus 8 into 0.35. That is equals to 6.5. Effective nuclear charge on F negative is equals to ZF minus screening constant, that is equals to 9 minus 4.5 is equals to 4.5. According to Pauling, the radius of the Na positive and F negative ion can be evaluated from equation as Rna positive is equals to 6 upon 6.5 and RF negative is equal to 6 upon 4.5. Substituting the value of 4 and 5 in equation 3, we get C upon 6.5 plus C upon 4.5 is equals to 2.31, and by solving this, C is equals to 6.41. Using the value of C, RNA is equals to 6.41 upon 6.50 is equals to 0.95 Armstrong. RF negative is equals to 6.41 upon 4.5 is equals to 1.36 Armstrong. Using this procedure, one can find out the radii of cations and anions of a number of ions, size of the cations and the anions. Ions are formed by the loss or gain of electrons from the outermost shell of the atoms. In case of cations, the size is invariably smaller than the parent atom. This is because with the removal of electrons from the atom, the magnitude of the nuclear charge remains the same while the number of electrons decrease. As a result, the electron exert more attractive force for the remaining electrons. In other words, the nuclear charge per electron increases and the electrons are strongly pulled towards the molecules. This results in the decrease of the size of the resulting ion. When more than one electron is lost from the atom, the effective nuclear charge increases substantially. This results further in the decrease of the size of the resulting ion. In case of anions, the size is always larger than the parent atom. This is because with the gain of electrons in the outermost shell, the total number of electrons increases, whereas the nuclear charge remains the same. As a result, the same nuclear charge is now exerted upon number of electrons. It means the effective nuclear charge per electron decreases and thereby the force of attraction between the nucleus and the electrons decreases. This results in the increase in size. Periodic trends in ionic radii of isoelectronic ions. Ions which contain the same number of electrons but differ in the number of protons in the nucleus are called isoelectronic ions. Van der Waals radius. Before we discuss van der Waals radius, it is important to distinguish between intermolecular and intramolecular forces. Intramolecular forces are forces that are responsible for the formation of a chemical bond, whereas intermolecular forces are weak attractive forces between atoms. Intermolecular forces hold two or more atoms together are often called van der Waals forces. For example, iodine is a solid at room temperature. The force that holds the molecules together in the solid are the van der Waals forces. It is one half of the internuclear distance between the adjacent atoms belonging to two neighboring molecules of an atom in the solid state. Thus, it is one half of the distance between two bonded atoms of two adjacent molecules in the solid state. Van der Waals radius corresponds to the closest approach of two atoms. R van der Waals is equals to internuclear distance between two non-bonded nearest neighboring atoms divided by 2. The van der Waals radius is a non-bonded type of radius for an atom with a closed configuration. Therefore, it is not surprising that van der Waals radius of chlorine is essentially the same as the ionic radius of chloride ion. The ionic radii of the non-metals generally can be taken as reasonable values to be used as van der Waals radius. This is because both possesses a complete octet of electrons are shown. A comparison of the van der Waals radii with the covalent radii of the atoms clearly show that van der Waals radii are longer than covalent radii. This is expected because in the formation of a covalent radii, the force existing between two non-bonded atoms are weak. As a result, the atoms are at large distances from each other. Therefore, van der Waals radii greater than covalent radii.